Right, so this talk is about GELI support for EFI. Of course, the necessary disclaimer, this is not the position of any organization or company. This was done by me, not for any employer. Now that's out of the way. So what is GELI? It is a block level disk encryption scheme native to FreeBSD. I believe there's some support on some other platforms, but it originated from FreeBSD, grew out of the GEOM subsystem. So it's been supported in user land for some time. So you could have partitions that or GELI encrypted partitions that were mounted at boot time by the normal system. Full disk encryption, meaning your entire disk is one big GELI volume or a bunch of GELI volumes, was not supported until recently. Alan Jude added it for x86 BIOS. UEFI, of course, is the modern boot system that replaces on many systems x86 BIOS. And it is quite different from that system. So if we want to support GELI going forward, we need EFI support. So a bit about EFI. It's UEFI, that's Unified Extensible Firmware Interface versus the original was Extensible Firmware Interface. I use them interchangeably. So it is a higher level boot system. It provides, instead of the very low level sort of assembly and I/O ports based stuff that BIOS does, it has an abstract API, and you use this to talk to devices, allocate memory, register drivers, and whatnot. You do not have the direct access to memory, so you can't just grab some memory address and stash data there and expect it to work, and you can't just go directly after devices the way you can in x86 BIOS. So the boot process, the firmware is expected to find something called an ESP, which is basically an MS-DOS file system, guaranteed to be at least as big as 200 megabytes. So that's quite a bit larger than what you have with BIOS. And the FreeBSD implementation of this has two steps. There's boot 1, which is that is installed to the ESP, and its sole purpose in life is to find loader. So it goes off and hunts down checks all the partitions until it finds the loader program, and then it invokes some image loading APIs to load that. Loader then, of course, is your classic boot shell, your loader prompt and your little logo, ASCII logo. So first, what are the core challenges that went along with this support? So like I said, UEFI is different, much different from BIOS. There are some benefits and there's some challenges. I'm not going to go through each of these right now because I'm going through them more in detail. So first is in BIOS, you have a multi-stage bootloader, and you have this challenge of I need to get my keys that I detect a GELI partition, I ask you for your password. I then have further stages of loader, and I have the kernel, and I need the naive way of doing this is I ask you at every stage, and that would end up asking you for your password 3 times. That's obviously not what we want, so we need some way of getting the keys, obtaining the keys in one stage and moving them down the line. In the BIOS, of course, you can do whatever you want with memory. So I believe it just shoves them onto a stack frame. Alan's nodding. That is correct. So BIOS just says, okay, I'm starting loader. I'm going to shove a bunch of stuff onto the stack, and then loader knows that I've done that and will find it and pull it in, and everything's fine. EFI has no such thing, and there's no obvious way of doing that. And then, of course, there's getting things into the kernel. When x86 BIOS GELI support was added, the solution was it stuffed it into an environment variable, and then crypto pulled that out so that it doesn't show up in in the kernel environment and leak your password. But we wanted a better way of doing that. So another problem is that, and this is really more just an issue of dealing with FreeBSD EFI support. So loader.efi is still based mostly on the loader code base, which uses libstand, which is this kind of minimal standalone C library for those who haven't done loader work. Think of it like libc without an operating system, basically. Boot 1 was this minimal thing that had its own entire code base, and there's quite a lot of code duplication there. So any change would end up basically with these two parallel implementations, and one of which is really awkward because boot 1 is very, very minimal. And finally, the GELI driver architecture itself. So GELI, of course, is based on geom, which is this abstract you can, I believe, stack up however arbitrarily complex of disk partitioning and encryption structures as you want. You could have like a GPT table and then a GELI and then another GPT table and something else. Yeah, right. So loader.efi kind of allows you to have sort of a one-tier system. You can have a partition table, you can have a GELI volume, but that's about as far as it'll go. And boot 1 was just completely flat. It expected to get a device handle that's a partition, and there's a file system. And it did not have any ability to support anything else. So moving on to the actual project history. So rough timeline of how the work went. I think of it as there were basically sort of a pre-stage, and then there's two actual stages. And then we are where we are here, where we're basically trying to get it committed. So the first stage, at this point, I had recently finished support for a ZFS EFI boot and thought it'd be really nice if I could encrypt my hard drives. So I started out thinking I'm going to kind of feel this out and rough out some kind of a proof of concept and see where this goes. So the first obstacle I ran into was that issue with boot 1, that it really has nothing resembling geom at all. And if you're adding this encrypted partition scheme, you have to. So I started working on this providers framework and actually got that done and working, and that really highlighted the problems with the split code base. So at that point I said, all right, I'm going to throw that away, and I'm going to do this right, and I'm going to try and get these code bases unified. So a bit more about EFI drivers. So EFI has this mechanism by which you can create your own drivers, and the thing you use to do anything is a structure called a device handle, which is sort of an abstract. This represents a something, and then I pass that into functions, API functions that represent some interface. And you register. There's a number of interfaces, and when you write a driver, you can register some number of these on a given handle. You can also create new handles. So this looks a lot like what you want when you're building, GELI support. Looks similar to geom. Also, one caveat: the EFI spec guarantees you have an MS-DOS driver, MS-DOS FS. It will attach it's a simple file system interface. It will attach that to anything where it smells an MS-DOS FS. So, like I said, this looks a lot like geom. Also, it looks a lot like what libstand was presenting. So my first thought was, well, we have an EFI loader. Why don't we just actually make it EFI and base everything off of that, and rewrite what we have to inside loader to make that work. So I created completely cut down boot 1 to just basically, I'm going to find anything. I'm going to register a bunch of drivers, and I'm going to look for any instance of an EFI simple file system and try to load from there. That was nice. On the loader side, I created these 2 shim drivers. One, I found you couldn't completely remove the libstand interfaces. They're too deeply embedded in everything, and would be quite a bit of work and probably not worth it to pull those out. So I created basically 2 shims. One converts the EFI simple file system interface into the libstand POSIX-like interface, and then the other one is the other direction. And the idea is that loader and all of its existing code continues to think it's using libstand. It's really sort of talking through these shims down into EFI. So this has some benefits. Do I talk about that? Right. One is that GELI can just be an EFI driver. And this ends up solving the problem of passing keys, because once an EFI handle is created, it's there, and as long as I'm in a bootloader, I still have access to it. So I can create my my EFI handles representing my GELI partitions, probe those for file systems, and then load loader past that, call into loader, and all that stuff's still there, and I don't have to reprobe. I don't have to ask for passwords again. It also sort of sets the stage for hot probing devices at boot time. And I almost got there, but I didn't quite, because Bcache came along halfway through this work. And Bcache architecture is fundamentally built around Bcache is a boot time block cache. It's fundamentally built around the idea that I detect all my devices, and then I set up a cache, and then I do all my I/O. And it does not want to have new devices showing up after that mode switch. Right. Yeah. So as I mentioned, this gets around the problem of passing keys from boot 1 to loader, or passing GELI information from boot 1 to loader, because you use the same handles that boot 1 created. You still have the issue of getting keys into the kernel. So this is where keybus comes in. So at some point, loader has to obtain all the keys still, and then provide them to the kernel. And previously, this was through the environment variable, but that changed. But it also has to have a way of actually getting the keys. So EFI has one of its many interfaces is a KMS device. So that's basically a device that looks like a hardware key management system. The idea being you put your keys in, and then you can retrieve them through this API. So this works really well for being a key store. So I implemented basically an in-memory key database that presents itself as one of these. And loader will, when it's about to boot the kernel, loader goes looking for this KMS, pulls the keys out, and then supplies them to the kernel. And when boot 1 or loader is loading its drivers, it sets up one of these. And when GELI acquires a password, it puts that key into this database. So that's how that worked. Also, I added a new interface for getting keys into the kernel. I call it keybufs. Is that next? Yeah. So keybufs was an improvement on how to get keys into the kernel. So when you're booting a kernel, you can supply sort of arbitrary metadata as information that gets that is then available to the kernel boot procedures. This is used in a couple of places. The one I know about is it passes a bunch of EFI console information with EFI. So I added this new kind of metadata called the keybuf that has By default, it can deliver up to 64 keys, and it's big enough to be a 4096 RSA key, though I don't use that yet. Keys have a tag, so they tell you what kind of key they are. Right now, the only tag is a GELI key. And then when crypto does its initialization, it picks up these keys and does whatever it needs to do with them. So what that means for GELI is that those keys are stashed somewhere, and then whenever you try to attach a GELI partition, it checks that table, and if it already knows the key, it doesn't ask you for it. So that completely solves the key passing problem.
And it means we don't pass the key in plain text anymore.
Right, that too. Also, it's not in an environment variable, which could be risky. So there's, of course, this is an encrypted file system. I have to get the crypto from somewhere. Alan had, when he did the x86 BIOS work, pulled in a minimal set out of the kernel crypto. The reason for that is that x86 BIOS is very space constrained, and so you can't necessarily pull in every cipher. I created this boot crypto framework, which will probably at this point be replaced by something better, but at the time I thought we might be living with that decision for a while. So I created something designed to pull in more ciphers. Right. Given that there's active talk of overhauling crypto, I'm not going to talk as much about that as I planned. So I also thought ahead with this KMS device. I was thinking ahead, what if we have readily available and trustworthy hardware key management systems? And there's a pretty simple solution. There's an easy solution for this. So my little in-memory database says, okay, well, there's already a KMS. I'm not gonna work. To GELI, all it knows is that it has some device that talks to this interface. So nothing changes there. That just works. Whatever boot crypto stuff is available would need to be, it would need to get its keys or else maybe ask a thing to encrypt something for it. And then instead of actually passing the keys, you might pass in identifiers into the kernel and just leave the keys in this hardware key store. Right, so that gets us to the end of the first stage. As I said, the EFI, I call this the EFized approach, was turn everything into EFI. It had benefits, and it also had some drawbacks. So benefits were that boot 1 became very minimal. The duplicated code base is completely gone. You had very nice integration with firmware-provided drivers, so firmware could provide something with an EFI simple file system interface, and you could use it if you're booting off, something like GRUB. We can drop the MS-DOS-FS driver, and of course we had the groundwork for hot plugging. There were also drawbacks. So one thing I found and have come out of this knowing now is that EFI doesn't do a very good job at supporting non-Microsoft interfaces and systems. EFI simple file system interface believes the world is MS-DOS-FS, and a POSIX VFS file system doesn't quite work that way, and there were some awkward, bits about that junction that didn't quite line up, and as a result, some information got lost. So if you were to take that code and go into your boot shell and start poking around and using some of the features, you'd get weird things about directory listings, and you'd be missing timestamps and whatever else. Also, the ZFS boot environments were completely lost when in the translation there, so that wasn't going to work. So at that point, there were also some breaking changes that made it into head, and this code had started to have some problems. So I backed away from the EFized approach and took a simpler tack on this. So dropped one of the shims entirely. The other shim is still out there as its own code review. Boot 1 had previously used EFI APIs to do its work. I rewrote Boot 1 again and made it use libstand. And this it's recovered quite a bit of the simplicity, got rid of a lot of code. The casualty of this, of course, was that the groundwork for hot pluggable devices is not there. That could probably be recovered with enough effort, I think. So, what do we got here? Yeah, so these are just an overview of some of the code changes that made it into a head while all this was going on. So, EFI part is a driver. It handles partitions. It got refactored quite a bit. It was split up between hard drives, floppy drives, and CDs. That was incompatible with the older structure of that code. One thing that I had to revert is somebody at some point was manually parsing partition tables inside the EFI part driver. And if your master partition is GELI encrypted, that clearly will not work. You're attempting to parse an encrypted partition table. So the testing and review and how all this got in. So key buffs went in back in, what was it, April? April or May or somewhere. So if you're using a recent 12 kernel, you have key buffs. And I didn't intend it this way, but it turned out that was absolutely the right way to do it, because now any changes to loader or boot will just work. You don't have to rebuild your kernel, and it also made it much easier to test things because I was using recent kernels and I didn't have to do anything. The legacy environment variable method still supported and will be for some time. It will be phased out in some sensible way eventually. But it will probably always be zeroed out so that nobody accidentally leaks a password. So to test this stuff, I set up a bunch of QEMU images, a bunch of different combinations. I've been personally using a root on ZFS EFI booted laptop for quite some time. So I was actually brave enough to test this on real hardware. I had a flash drive that I'd been using as an L2 ARC cache. So I sort of went halfway and said, I'm going to GELI encrypt that. And if it bombs out, then I can still boot because I can say, don't use the cache. Just get me back to running. And then fix whatever I needed to fix. So after enough testing of QEMU images and found a few bugs, in EFI part, actually, I finally took the plunge and converted that laptop completely over to a fully encrypted GELI root ZFS inside GELI. And it worked, except that when I ZFS sent all my data because I had to completely blow the pools away and recreate them, but I forgot the -r flag, so I only ZFS sent my root directory. So currently we are working on getting this in. It won't be long. You can use it. If you really absolutely have to have it, you can pull my GitHub GELI branch and you can have it. So plans to fill out support for this. GRUB is apparently the best way to get a Coreboot support. So I have plans to add the key buff support into GRUB. I've talked to their developers. It doesn't seem like it'll be terribly hard. As for longer-facing plans beyond this, I have a general agenda of security and tamper resilience-related topics. If you've talked to me this weekend, you've certainly heard about these. So at that point is the end, and I'll take questions.
So you indicated that you support both a disk with a GPT partition table with a GELI encrypted partition. That's like what the installer does.
Right.
That works. But you said something about a disk where it's completely GELI encrypted, and then you have a GPT partition inside the encrypted one?
I
wouldn't be
actually
able to
don't
boot
know
off
if
that.
Loader can do that.
Yeah, you wouldn't be able to boot off that.
I don't think Loader can do that. EFI, because I'm creating a device handle and then probing it, EFI will go, aha, there's a GPT there, let me set that up for you. I think if you were to try that Loader would fail somewhere in naming the devices.
Right.
It cannot build the data structures it would need to represent that. That's the problem. It could be probably patched relatively without too much trouble to do that, but that would be mainly targeting the way that Loader represents internal data structures and partitions.
Right.
The actual mechanism for that, Loader assigns, if memory serves, I don't think it actually builds a data structure, it just names things. So it gives it a string, and then later it parses that string. So if you were to modify the string parsing and figure out what this is and where to find its handle, I believe, actually, when they refactored EFI part, it does have a data structure. It has like a 2-level list and then partition tables. So there'd be a little work there, but it could be done.